Today I will talk about quantum mechanical calculations of electron interactions and dynamics in condensed matter. Okay. So my group works extensively on this topic. One goal is we compute the interactions between the electrons, spin, the atomic vibrations, so-called phonons, and other excitations. And with these interactions, we study various physical phenomena. One of them is charge transport, where we try to accurately predict the electrical conductivity and the scattering mechanisms that govern it in various classes of materials. Another topic which I will not discuss extensively today, we study materials excited out of equilibrium and the ultra-fast dynamics that follows. And a more recent effort that I will discuss today is studying spin dynamics in materials, which is a topic that has both fundamental and applied reasons for being studied and interesting. So my group also develops an open source code called Perturbo that makes these workflows available to the community. Okay, so the plan today is to take a deep dive into selected aspects of this picture, focusing both on the physics and on the computational methods. Okay, so I think that studying electron interactions and dynamics is a prime example of model reduction in quantum mechanics. Okay, so on one hand, you have the many electron problem, where if you want to solve Schrödinger's equation and compute the many electron wave function, this is a problem that is exponentially hard. However, we circumvent that by focusing on low-rank quantities, such as the electron density, which is a function of one electronic coordinate, and the Green's function, which is a correlation function of the electrons, and it's a function of two electronic coordinates. With these two quantities, first, we compute the ground state using density functional theory, which is a method that is centered on the electron density. And then we use that as a starting point to then describe the electron dynamics using Green's functions and many-body theories. This framework allows us to study electron interactions and dynamics from first principles, which means that the structure of the material is the only input, and everything else is computed from quantum mechanics without using any free parameters in the theory or any other input from experiment. So density functional theory, we use it as a starting point to describe bonding and ground state properties in materials with a good trade-off between accuracy and computational cost. And then on top of density functional theory, we develop Green's function and many-body methods to study electron interactions and dynamics. So today we'll focus on three problems. The first one is computing the interactions between the electrons and the atomic vibrations, or so-called phonons. Also the interaction between the electron spin and the phonons, and the interactions between the electrons and defects in materials. With this information, I will show you various studies of transport properties, spin dynamics, and other non-equilibrium physics. So let's start here with the electron-phonon interactions, which are really pervasive in condensed matter. In the context of transport, they're important because they govern transport near room temperature over a wide temperature range. The idea is very simple. The atoms move due to their thermal motion. That motion perturbs the periodic potential seen by the electrons in a solid, and that perturbation causes the electrons to scatter. So an electron in a solid, initially in a state with a given band n and crystal momentum k, gets scattered into a different state by emitting or absorbing a phonon with a given momentum q. So the central quantities in the theory are the probability amplitude for these scattering processes, which are the electron-phonon coupling matrix elements. These quantities are difficult to obtain from models. The reason is that you need accurate wave functions and phonon data. However, using the density functional theory formalism, we can obtain these coupling matrix elements and resolve them for different electronic and vibrational states. As I will show today, ultimately, we end up using billions or sometimes even trillions of these interactions. So these are not really minimal models. However, in this framework, these are not fitting parameters. They're actually computed deterministically. Once you have these matrix elements, for example, you can compute the time scale for these scattering processes. This is the so-called relaxation time, which you can obtain using Fermi's golden rule. Or when the electron-phonon interactions are weak, you can study transport in the framework of the Boltzmann equation, where the electron is seen as a wave packet that scatters with the phonons, and that process limits the conductivity. In the framework of the Boltzmann equation, you can compute the conductivity without using any free parameters, or the mobility, which is the conductivity divided by the carrier density, and it's a quantity that is often measured in the experiment. What's important actually is that if you want to validate the accuracy of your electron-phonon interactions, one way to do it is to compute transport and then compare it with experiments. Just to give you an idea of how these calculations are done, the starting point is density functional theory to obtain the electronic structure, and then the linear response version of density functional theory, which is also known as density functional perturbation theory, used to compute phonons and the electron-phonon perturbation potentials. Now, in principle, now you have all the ingredients to compute the electron-phonon coupling matrix elements. However, the challenge is that to compute transport properties and dynamics, you need to fully converge these scattering processes, and that requires extremely fine grids in momentum space. These are typically grids of order 100 by 100 by 100 for both the electron and the phonon momentum. So this leads to these very large matrices with billions or trillions of entries. These very fine grids cannot be accessed with direct DFT calculation. And so the typical workflow is that you first compute this electron-phonon coupling with grids of order 10 by 10 by 10 for both the electron and the phonon momenta. And then you interpolate onto these fine grids. The interpolation is very subtle. The idea is that you first transform these quantities to a localized basis, where now the physical meaning of this coupling are they're essentially the probability amplitude for the scattering between two localized orbitals at a distance RE away due to a perturbation at a distance RP away. Now, for most phonon modes, these interactions decay rapidly, so they're short-ranged. In particular, they decay into the Wigner side cell associated with these coarse grids. Therefore, it's as if you computed them everywhere in real space. Then you can do a double Fourier transform and obtain them on arbitrarily fine grids. Okay? Now, the density functional theory calculations are standard. They can be done with a standard DFT code like quantum espresso. However, forming the matrix elements, interpolating them, and using them to compute dynamics, that's a much more specialized workflow. And for that, we use our own code, Perturbo. Just to give you an idea of something that's simple, now with a calculation that takes only a few minutes, you can compute the resistivity in a simple metal like copper, gold, or silver, or the mobility in a simple semiconductor like silicon, and get results that agree well with experiment without much effort. This is basic. However, if you start going into more complex classes of materials, there's basically many challenges that makes these calculations complex. In particular, electron-phonon interactions range from weak to strong. In the weak limit, band theory and the perturbative picture that I have described work. However, the electron-phonon interactions can be short or long-ranged, and the structure of the material can make them more complex. As the electron-phonon coupling gets stronger, the carriers couple strongly with the lattice, and they form polarons, which are electrons that travel together with their lattice distortion. And polaron physics requires non-perturbative and different methods. Finally, regardless of the strength of the electron-phonon coupling, what can happen is that the electrons interact strongly with each other. That's typical of so-called strongly correlated materials. In that case, your starting point density functional theory may actually fail. So I will show you in the next few slides how we've made progress on tackling these problems over the last few years, and that now allows us to study electron-phonon interactions in much broader classes of materials. Okay, just take a sip of water. Okay, so the first challenge is that in materials with polar or ionic bonds, as the ion moves, they generate long-range electron-phonon interactions. And so the framework to interpolate the matrix elements that I've explained earlier fails. These long-range interactions can be apportioned into a dipole and a quadrupole term. The dipole term is the well-known Fröhlich interaction due to the longitudinal optical, or LO phonons. As these phonons vibrate, they behave like oscillating dipole, so they emit a long-range field, and the coupling goes like the inverse of the phonon wave vector. So in this paper, in 2016, we have shown how to compute these Fröhlich matrix elements from first principles. In particular, we have shown that you can first subtract them on the coarse grid, then you can interpolate the short-range part, and then you can add them back on the fine grid. And that allowed us to compute the transport properties, in particular the mobility versus temperature of a polar material, gallium arsenide, entirely from first principles. That calculation shown here with the solid line agrees extremely well with experiment, and we can also compute the relaxation time for an electron to emit an LO phonon. The time that we predict is about 168 femtoseconds, which agrees extremely well with the experimental time of 165 femtoseconds. So that's a first indication that these methods can actually provide quantitative accuracy. More recently, we've also shown how to include the quadrupole term, which is particularly important in piezoelectric materials, which are ionic, non-centrosymmetric materials. Again, here the strategy is you first identify what the quadrupole term is, then you subtract it on the coarse grid, and then you add it back. And as we show here, for a typical piezoelectric material like lead titanate, if you don't include the quadrupole term, like is shown here with these blue lines, particularly for the acoustic phonons, you make very large errors. So now we can include both of these terms, and this allows us to study broad classes of polar and ionic materials, in particular oxides and perovskites, which are interesting for both fundamental and applied reasons. However, one of the challenges is that these materials are structurally complex. In particular, many of them have structural phase transitions. A typical example is strontium titanate, which is a cubic perovskite near room temperature. And then below 100 Kelvin, it distorts to a tetragonal structure. Now, the atomic vibrations, so-called soft phonons, that are responsible for this distortion are notoriously difficult to compute from first principles. Reason is if you try to do a phonon calculation in the high temperature phase, this density functional theory is a zero temperature method, it sees these modes as dynamically unstable, as shown here with these negative frequencies. So to circumvent this problem, in this work in 2018, we have used a temperature-dependent effective potential method, which at each temperature builds an effective quadratic Hamiltonian that makes all the phonons stable. With that method, we've been able to predict all the phonons, including the soft ones, in very good agreement with experiment. And then we've been able to study also the coupling of the electrons with the soft phonons, which would not be possible if you just use density functional theory. What we found is that in strontium titanate, but this is typical of many perovskites, the strongest coupling is still with the yellow phonons because they're polar. However, the second strongest coupling is with the soft modes. And you need to include all of them to carefully explain their transport properties. In particular, this has allowed us to resolve an open question in this material, cubic strontium titanate, where in experiment it's known that its mobility goes like temperature to the -3, but the origin of this trend was debated. So our calculation that includes all the coupling with all the modes using the Boltzmann equation can accurately predict this trend. You see we get temperature to the -3.1. We have shown that you can show basically unambiguously that this is due to a competition of the scattering with the LO phonons at room temperature and with the soft phonons at lower temperatures. If you don't include the soft phonons, you actually make very large errors. And so developing these quantitative models basically allows us to less ambiguously determine what are the microscopic mechanisms that govern transport. Now, if you notice carefully here, the temperature trend is fine, but the mobility that we predict is still an order of magnitude greater than experiment. And so that has led us to think about the fact that in many of these polar materials, the electron-phonon coupling is stronger than can be treated with the perturbative methods that we have discussed so far. In particular, as I've mentioned, the electron-phonon coupling gets stronger. You form polarons, which are electrons carrying the lattice distortion. And including polaron effects in these first principles theories is not trivial. As a first step, we have adopted this cumulant approach, which basically make an ansatz where the interacting Green's function is equal to the non-interacting one times e to a function that you call a cumulant. Okay? Without going into technical details, the idea is that you put the lowest order electron-phonon interactions in the cumulant. But now, because this is exponentiated, now if you think of Taylor expanding this, then the Green's function will basically include all sorts of higher order electron-phonon coupling processes. And therefore, there's hope that it would also include polaron effects. From the Green's function, you can obtain the spectral function of the electron. And we do this for strontium titanate for a state near the bottom of the conduction band. So this quantity, the spectral function, is basically the density of states for a single electronic state. And so for this state here, you basically, because this is the density of states, you would expect to find a peak here at the band energy. And at this peak, maybe with a little bit of thermal broadening. However, due to the strong coupling with the LO phonons, now we see the appearance of these two satellites that are spaced by the energy of the two LO phonons, and they're basically a signature of the strong coupling and polaron effects. These satellites can be measured in photoemission experiments, and in strontium titanate, if you see this is the bottom of the conduction band, experiments finds a pronounced satellite about 100 millielectron volt below the conduction band, which is in very good agreement with our most intense satellite here due to the strong coupling with the LO1 phonon. Now, equipped with these accurate spectral functions, we can do calculations of transport that are fully quantum mechanical, so they go beyond the framework of the Boltzmann equation. In particular, we use the Green-Kubo framework, where the conductivity is computed directly from the spectral function. So it also includes the effect of these satellites and all these polaron effects. When we use this level of theory in strontium titanate, you see that the mobility drops by about an order of magnitude. And now both the temperature trend and the absolute value of the mobility are extremely close to experiment. Again, this is a theory that does not have any free parameters in a complex materials that has polaron effects. And so we believe that this is a great success for these first principles theories. Since then, this has allowed us to study various oxides and organic crystals with polaron effects. But I think that the microscopic aspects of transport that one can extract from these calculations are at least equally as interesting. For example, here, if we study this integrand, basically we see that as temperature increases, and in particular at room temperature, the Polaron satellites contribute to transport by as much as 50%. So what this means is that the picture where transport is limited by the scattering of the electron, that semi-classical picture basically breaks down, because to have the particle, you will need to have a very sharp spectral function.
Just one question. Do you get the Polaron forming in the system just by using a local functional?
In this
from a hybrid functional, your calculations?
No, I believe this is just PB sol.
And do you get a Polaron in the system?
These are large Polarons. So it's not a small Polaron done with like a supercell. This is basically done with this cumulant. And then what we find is that the bands are renormalized. Basically, in this calculation, what we do is we compute the spectral functions for all the states in the bands. And then if we follow these peaks, it basically gives us a renormalized version of the DFT bands. So in that sense, we find a mass enhancement and therefore Polaron effects.
Yes, I can ask. How can you really be sure these are Polaron effects just by including? I guess I didn't fully understand how are you including in your cumulant the information from the
yeah. So basically, in the cumulant, you put the lowest order self-energy. And so this basically gives you all the, it's like this self-energy here. So when you do it in the cumulant, it basically gives you the inclusion of all these improper diagrams where at order n, this self-energy is repeated n times. So this is one family of diagrams that are higher order. And it basically shows that these higher order effects are important. And so this is what we called Polaronic effects, because they basically go beyond the lowest order theory. But in general, these satellite peaks and their appearance here, this is usually a signature of the Polarons.
But you cannot really decompose it to see which are actual branches of your phonons that are contributing to.
This is mainly the LO1 and LO2, because the spacing, in this case, it's very clear. We've also done this for organic systems, and there it's really a combination of modes because you have many modes, basically. But for polar systems, it's usually the LO phonons, and we know that they basically have the strongest coupling, so this is kind of expected in a way. Yeah.
Do you see much difference if you use PBE instead of PBE sol?
I think PBE sol leads to better structures, and so this is why we use it. It basically leads to better phonons, but there's nothing too fundamental. In some of these systems, PBE might try to swell the system a little too much, but yeah. Okay, excellent. Feel free to ask more questions at any point in the talk. So in fact, I wanted to provide further evidence for this statement. So we're saying that if there's strong coupling and a polaron and the satellites are contributing, you're no longer in this picture where you apply an electric field, the electrons accelerate, scatter, and that limits transport. To study that, what you can do is we basically can compute the optical conductivity, and from that we can extract an effective scattering rate. We don't have access to scattering rate because this is not a perturbative method. Now, if you have a semi-classical scatter that scatters with a relaxation time tau, and each time it scatters, it exchanges energy delta E, which for phonons is kT, then because of the uncertainty principle, if you write the scattering rate in energy units, that scattering rate has to be less than kT for that picture to hold, okay? This is called the Planckian limit for transport, and you could view it as the maximum energy dissipation rate for a semi-classical scatter. These are the effective scattering rates that we extract from the conductivity for strontium titanate. And you see that as temperature increases, you get more phonons, the Polaronic effects become more important, and basically in the same regime where the satellites contribute extensively, you have that the system breaks this Planckian limit. Doesn't mean that any physical law is being violated. All it means is that you can no longer regard transport as being due to the scattering events of a particle. It's more of a collective effects that involves these higher order terms. So you could say that this is a quantitative way to find signatures of strong electron-phonon coupling and Polaronic effects. Okay, to conclude the topic of electron-phonon coupling, I also wanted to show you the case where it's the electrons that couple strongly, in particular in so-called correlated systems, which are typically materials that have open D and F shells. The electrons interact strongly in these localized orbitals. And typically, density functional theory often fails to correctly describe the ground states of these materials, at least in its basic flavor. There's a couple of ways to study correlated materials, two that I've highlighted here. One is the Hubbard-U extension of density functional theory, also known as DFT plus U. A very different one is dynamical mean field theory. And currently, we're developing electron-phonon calculations within these two levels of theory, but I will discuss only the first one. Again, the reason for studying these materials is that these are probably some of the most intriguing systems. They can be mod insulators, high-temperature superconductors, multiferroics. So obviously, adapting these theories to work for these systems could provide quantitative insight into their physics. So in this recent work, unfortunately, it's getting cut off, but this is a PRL in collaboration with Nicola Marzari from 2021. What we did is we computed electron-phonon interactions within density functional theory plus U. The idea is that you add this Hubbard-U extension, this Hubbard-U piece of the energy, which, loosely speaking, puts an energy penalty for doubly occupying orbital because of the strong local interaction. Now, with this method, we have studied a prototypical mod insulator, cobalt oxide. In density functional theory, this is predicted to be an unstable metal. However, in DFT plus U, you can correctly characterize the antiferromagnetic insulating character. So this is a polar insulator, basically, that is also antiferromagnetic. And then we've implemented electron-phonon calculations within density functional theory plus U. There's a couple of things that we found. The first one is you need to add the Hubbard-U term to recover the long-range Frawley coupling with the allophonons. That's because in DFT, the system is a metal, okay? Within density functional theory plus U, we can correctly describe the long-range interactions. The other interesting story is that the perturbation that is now due to the Hubbard potential is actually essential to describe the spin-dependent electron-phonon scattering in the open D shell. This system realizes probably one of the most complex regimes where both the electron-phonon interactions and the electron-electron interactions are strong. So it's strongly correlated, but also it's polar, and the coupling with the allophonons is strong. So if you apply the cumulant and study the spectral function, we see these very strong peaks due to Polaronic effects. And so we believe that the combination of these tools now gives us access to studying Polaronic effects in various families of correlated materials like cuprates, ruthenates, and we are in fact working on some of these systems. Polaronic effects in these materials have been conjectured to be connected with high temperature superconductivity and many other exotic physics. And so it's very exciting to be able to study these effects with more quantitative tools. Okay, I would now like to transition to Spinphonon interactions. So the electron spin is a variable of very high interest. You could think of having so-called spintronic devices where you control spin currents instead of charge currents. But also in the electron spin, you can encode quantum information. And that's been used, for example, in semiconducting spin qubits, where the hope is to encode quantum information in the electron spin and ultimately to assemble them and make quantum computers. If that's the goal, then basically the most detrimental physical mechanism is spin decoherence. Basically, there are various effects due to the environment that scatter and relax the spin. There are various mechanisms for spin decoherence. One of them is nuclear spin. There's noise. There are others. But the one that you can never remove is the one due to the phonons, okay? Because it's inherent in being at finite temperatures. So with phonons, usually there's a couple of mechanisms. One is the electron spin can be scattered due to a phonon, and the flip can spin in the scattering process. This is the so-called Elliott-Yaffe mechanism, and the spin relaxation time is proportional to the electron-phonon collision time in this mechanism. The spin can also precess in the spin-orbit coupling field, and that is also a source of decoherence that is called the Dyakonov-Perel mechanism, where the spin relaxation time is now inversely proportional to the collision time. So these two mechanisms are typically studied with models, and they're studied separately. However, they both have the same source, which is the spin-orbit coupling inside the material. Now, using Perturbo, we can form the electron-phonon coupling matrix elements in the presence of spin-orbit coupling. Now, these quantities encode the scattering amplitude between spinors. In practice, what we do is we use density functional theory using fully relativistic pseudopotentials, but then forming and interpolating these matrix elements is actually quite challenging. And so in this work, we have shown that we can manipulate these matrix elements in systems with spin-orbit coupling accurately. So in 2020, we used that as a starting point to study the Elliott-Yaffe mechanism. In particular, we computed these spin-flip electron-phonon processes, and then we used them by thermally averaging to compute the spin relaxation time in silicon. This formalism, which we call the spin RTA, does not include precession. And so it can only be used in systems like silicon, which is centrosymmetric, where the Dyakonov-Perel mechanism is not important. So this level of theory in silicon, as you can see here in this calculation in the solid line, can accurately predict the spin relaxation times over a wide temperature range. So this is encouraging, but ideally you would also like to include precessional spin motion. So recently, working with a student of mine, Jin-Soo Park, we've made significant progress on this problem. In particular, we have developed a method that we call the Spinphonon betasalpeter equation that includes on the same footing both the Elliott-Yaffe and the Dyakonov-Perel mechanisms. The Spinphonon betasalpeter equation is essentially a Dyson equation for the spin vertex. So if you apply magnetic field to a system, you have a susceptibility, which is the magnetic response. In diagrammatics, that's usually a bubble, basically. And the vertex of that bubble is the bare spin matrix. So this is just the spin operator in a block basis. Due to the electron-phonon interactions, this vertex gets renormalized with this function lambda that essentially takes into account both the electron-phonon scattering, and so therefore this includes the Elliott-Yaffe mechanism, but also, because of these propagators in this diagram, you also include spin precession between collision. And so both mechanisms are included. And the idea then is to solve this equation numerically, which actually is not too difficult computationally. It has a similar cost and algorithm to solving the Boltzmann equation for charge transport. Once you have this vertex function that corrects the spin, you can compute the spin relaxation times and also the spin precession rates. So now, for example, you can study both systems like silicon, where the Elliott-Yaffe mechanism is dominant and the Spinphonon BSC is still accurate here. But you can also study materials like gallium arsenide, where precessional motion is very important because it's non-centrosymmetric. In this case, the spin RTA is completely wrong. But with the Spinphonon BSC, you see that it can accurately predict the spin relaxation times over a wide temperature range. And so in this work, we have shown that you can do these calculations for both bulk and 2D systems for both electron and hole carriers. That's interesting, but the microscopic information that you can extract from this method is also very exciting. Basically, what it shows is that the vertex function strongly renormalizes the spin relaxation times. For example, in gallium arsenide, if you plot the spin relaxation time near the bottom of the conduction band, you see here that in the spin RTA, which we know to not work well, this basically vary rapidly with energy and ultimately diverge, which is unphysical. In the Spinphonon BSC, this new method, they're nearly constant, but they also show this oscillation with a period of the yellow phonon that couples strongly with the spin. What we can also do is we can artificially increase the strength of the electron phonon scattering by basically changing the matrix elements. And so if we plot the spin relaxation times versus the collision time, now for silicon, you see that this is nearly linearly proportional. But for gallium arsenide, this is almost inversely proportional. And so that's a signature that we can include both the Elliott-Yaffe and the Jakonov-Pearl mechanisms. So we can access these microscopic details, and we've planned to use this method in various materials and also qubit systems. What I find really interesting, and to me almost mind-blowing, is that if you look a little bit deeper into this vertex function, basically you realize that it provides a colossal renormalization of the spin dynamics. The reason is, for example, if you plot the vertex function in silicon, you see it has values of about 10 to the 5 that are weakly temperature dependent. And in other systems, we have found values that are between 100 and 100,000. Is that small or large? Well, for comparison, if you put an electron in vacuum and it interacts in quantum electrodynamics with the virtual photons, that process is known to cause a small change in the electron's magnetic moment. It's the so-called anomalous electron magnetic moment problem, and it was first worked out by Schwinger in the 60s. So if you take the electron's spin gyromagnetic ratio, which is 2 in Dirac's theory, it becomes 2 plus a little bit, and that correction you can call lambda. So the relative change, if you take an electron in vacuum due to the photons, which are intrinsic in the medium, is basically a vertex correction of about 10 to the minus 3. Now you take the same electron, you put it inside a material where now you have the thermal vibrations, the phonons. The resulting renormalization is much, much greater. It's the order of 10 to the 5. So it's basically 8 orders of magnitude greater. And so this is a proof that this is really a colossal phonon-induced effect that you have on the spin in solids. In this case, it does not change exactly the electron's spin, but it changes the spin dynamics. Okay, I would like to spend the last 5 minutes, if I have them, to very briefly, thanks. I'd like to talk about another type of interaction between the electrons and defects. So in all materials, you have crystallographic defects. In principle, you could compute these scattering matrix elements between the electrons and defects. What you could do is you could take a large cell in DFT, create the defect, take the potential, compute the difference with the pristine system without the defect. And basically, you'll be able to form these matrix elements and then retrace all the same theory that you have for the electron-phonon coupling. The challenge, however, is that you would need to use the wave function of this large supercell, which is not practical. And so as a first step to treat this problem with my student, Ite Lu, in the last couple of years, we have reformulated this method to use only the wave function from the primitive cell. And so you need the DFT calculation on the large cell only to extract the local perturbation potential. Now you can form these matrix elements. We've shown how to put them in the localized basis, interpolate them, and ultimately you can also compute defect-limited transport. This is very important because defects, different from phonons, they tend to govern transport at low temperatures. And also, obviously, in many materials, you intentionally add impurities called dopants to regulate the density of carriers. So now we have access to both low temperature transport and to also transport in doped materials. Why, I mean, is it needed? Like, do you really need first principles methods? Well, in empirical methods, you usually assume that there is some sort of a perturbation potential. But actually, you can see here that two different neutral defects in silicon, so a very simple system, a vacancy and an interstitial, they give very different scattering rates, and so very different residual mobilities at low temperatures. So the details of the microscopic short-range potential matters. Also, recently we have extended this to also treat charge defects. You need to include long-range corrections for that. And so with this method, now in the Boltzmann equation, we can include the scattering from both the phonons and the defects. That allows you to do two things. One is to compute transport from low to high temperatures. And then the other one in doped systems, this is silicon doped with phosphorus at room temperature. With this theory, we can also accurately predict the mobility as a function of doping concentration. So in a way, this now completes the dominant types of scattering mechanisms that you have in matter. Electron-electron is one that I have not mentioned that we're also currently working on. And so the set of tools that we have basically keeps growing and expanding. And so a couple of years ago, to address the community interest in these topics, we have released the first version of Perturbo. This is an open source code that is a broad platform for computing electron interactions and dynamics from first principles. We have recently released version 2 that has even more capabilities. So Perturbo allows you to compute electron-phonon and electron defect interactions. You can use it to compute transport properties like the conductivity, Seebeck, magnetotransport, or transport in high fields. These calculations now can be done on magnetic materials, systems with strong spin-orbit coupling, or enharmonic phonons. We have a relatively large user community. We now have over 350 users. And one of the aspects that make this code particularly appealing is that we've tried to develop it with modern standards of software engineering. For example, it's heavily parallelized, so it scales favorably up to millions of cores. It's also very easy to use, and we keep improving and expanding its capabilities. And so if you're interested in these topics, I would encourage you to download the code and try it out. And if I can show a final slide, which I believe is in the spirit of this workshop on model reduction. So the type of models that I've shown, I mean, I've said that they make this problem practical, tractable, but they're still expensive methods. So the question is, to do these calculations, ultimately, you need these coupling matrix elements on these very fine grids. These are billions to trillions of matrix elements. Normally, you don't write them because otherwise there will really be big data, thousands of terabytes usually. They're also in both the electron momentum K and phonon momentum Q. They're not particularly smooth, and they're also non-analytic. So it's very difficult to just interpret this data. Now, the question is, can we find more minimal models? Now, basically, the most compressed version that we have is the first step in the calculation, where we encode these matrix elements in a localized basis. Now, this has the same size of the matrix element on the coarse momentum grids, and it's usually very feasible. The memory cost is only about 1 to 10 gigabytes. So this is always the first step in the calculation. But the question is, can you use methods to even further compress the amount of data that you need? And so this is still unpublished work, so I cannot give too many details. But with my student, Yao Luo, we've used what I will call, in quotes, a data-driven method to basically show that you can reduce the data to about 5 to 10% of the size of this matrix and still obtain very accurate interactions. And also, you can further compress it, obtaining a speed up for the calculation of the electron-phone coupling on a fine grid. You can basically get speed ups up to 2 orders of magnitude while still retaining an accuracy in the observables of about 5%. So I think there is really great room for further improving these methods, compressing them using these new tools. Well, in some cases, these are old tools, but these methods are now becoming more relevant for first principles calculations. And so if these methods were to work, potentially you would need to revisit all the existing algorithms. And in particular, even for this simple calculation, the bottleneck has always been this interpolation and getting these matrix elements on the fine grid. Now we can show for this calculation that this is no longer the bottleneck with this compression by about a factor of 100. And so there is hope to find more of these nearly lossless compression algorithms. Okay, so in summary, I've tried to describe these approaches as an example of model reduction in quantum mechanics. This allows us to precisely compute interactions between the electrons, lattice, and spin. And with these calculations, we can interpret experiments and hopefully guide the design of new materials. I've tried to highlight 3 frontiers. One of them is Polaron, the other one is spin dynamics, and the third one is using machine learning and data-driven methods to further improve these calculations. Okay, thank you.